Well, getting near the end, let's look at something to do with strength. So this little man, who's about sort of this tall, can lift 3 times his body weight. So I think he's been Olympic champion 3 times. It would have been 4 times, but he changed nationality and he couldn't compete. So Suleiman Oglu is a rather remarkable weightlifter. It's probably pound for pound the strongest person in the world. But weightlifting is one of those sports where there is rather meticulous categorization into weight classes. There are certain sorts which don't have that, which you might have thought ought to. Shot putting we looked at earlier. You don't see many shot putters who are that big, and I think you can guess why. You won't get very far if you're a little shot putter. Another sport I was investigating in the last week, I discovered something interesting, is in the Paralympics, the wheelchair racing really ought to have weight classes. The dominant source of resistance for the motion at all distances is rolling friction, which is directly proportional to the weight being carried. And although there are meticulous regulations about the sizes of the chairs and the diameters of the wheels, there is none about the weight of the wheelchair. And the wheelchairs vary by at least 10 kilograms from competitor to competitor, and the competitors' weights vary enormously. And so there is an enormous difference between different competitors' total weight. And that really is the deciding factor about how fast they go. Well, what about strength? How does strength change when you get bigger, when you get heavier? Well, the strength does not change at the same rate as volume. Strength changes like a surface area, not as a volume. And you can understand that if you want to snap something like this piece of wood here, when you break it, you have to break through the molecular bonds in a cross-sectional area through one point. And I won't find it any harder to break those bonds at this point if this is a mile long or if it's just a metre long. So the total weight of this ruler, the total volume, is not relevant for how much strength is required to break this little slice of molecular bonds. So the strength of a material like that depends on a cross-sectional area, something with dimensions of size squared. And you've probably seen these familiar examples wandering around your home. The weight of something that grows, like a cat, grows like the volume, which is some measure of the size cubed. And you notice that strength does not grow at the same rate as R increases as volume. So when you have a little kitten, it's strong enough to hold its tail bolt upright like a spike. But as it grows into a bigger cat, the strength of the cat does not scale at the same rate. And so its tail tends to bend over. It's not strong enough to suspend its tail in that same way. So what you can see from these two things here is that strength is proportional to weight to the 2/3 power. So this is rather crude and simple. We could have done a lot better here if we wanted to. But what it tells you is that if you try to scale up on the same body plan, eventually you'll break. You won't be able to support your weight. So you can't have a giant the size of the Empire State Building. It will not be strong enough to support his weight. But this simple insight tells you you might be able to understand the world weightlifting records just on the back of an envelope. You see, the strength of a weightlifter is the weight lifted. And if we know the weight class that they're in, and they're very narrow, this simple rule ought to tell us how the world weightlifting records vary with the weight of the lifter. And if we do that, we really do quite well. So I've plotted weight cubed against weight lifted cubed against square of the weightlifter. So this is the 2/3 law that we were just looking at. And you can see that really there's a pretty good agreement. Okay, Weightlifters do some quite sophisticated mathematical things in trying to scale the performances of different weightlifters to the same sort of numerical coefficient. And to do that, they have to introduce a rather more complicated weighting for what happens with these very, very big, super strong weightlifters. Because these guys up here, the people that weigh about 30 stone, they don't tend to follow this rule. They're the weakest, relatively. If they did, they would break. And so you want to try and take that into account. But you can see, looking at a picture like this, you can decide who, kilogram for kilogram, is the strongest of all the weightlifters. But it's rather gratifying that this very simple proportionality allows you to understand what's going on. And it would also allow you to understand, if you looked at shot putters, of different weight, you can understand how their strength varies with their weight, and therefore how the launch speed is going to vary and how far they're going to throw. You can understand what the marginal advantage is being a giant shot putter as opposed to being a small one. And whether the shot putter of normal size throwing a little bit less might be actually intrinsically a superior performance. Well, finally, what's the maddest sport of all? So sixth formers and students are always interested in, what's the most extreme human experience that you can have? And if you ask people, they tend to think it's being an astronaut, it's being launched in the space shuttle or at Cape Canaveral or something like that, or being a high-performance fighter pilot. Actually, it's none of those things. The most extreme physical experience that anyone has is being a drag car racer. So the accelerations here are quite extraordinary. So you know how drag racing goes. It's over a quarter of a mile course. The winning times in the top races are about 4 seconds. Okay? So start from rest. Just to get a perspective, suppose you're in your drag car on the starting line at rest. Michael Schumacher comes past in his Formula 1 car at 200 miles an hour. You start from rest. You still beat him to the finish. So the accelerations are quite extraordinary. 6G, and health and safety is very problematic. So detached retinas are almost obligatory here. The deceleration is even more of a problem. Parachutes are thrown out the back and you decelerate very, very rapidly. You're also at the risk of serious ear damage if your muffs should fall off at all, or if you're watching. So the sound levels are extraordinary, and you're sitting in effect on an enormous tank of rocket fuel. Probably a large fraction of the total mass is this rocket fuel. So you get the general idea. This is, not really Sunday driving. It's American, that's why. But it's an interesting little mechanics problem. It's sort of problem that you don't see at school or undergraduate level. It's motion at constant power to a very good approximation. So if we just neglect the little bit of rolling friction at the beginning, which we can take into account if we want, that what's happening is the power, which is the force times velocity, which is mv dot times v. We'll forget about the changing m. You can add that in if you want. No problem, it still solves. And this is just a half m, missed out the m there, d by dt of v squared. So if the power is constant and you start from rest at t is 0, from x is 0, the square of the velocity is proportional to the time. Integrate again, the distance you travel in time t is given by this 3/2 law. And interestingly, if you turn this around as an expression for v in terms of x, you get this rule of thumb that turns out to have a name in the drag car business when numbers are put in old-fashioned units, and it's called Huntington's rule, which was just a sort of engineer's rule of thumb telling you what speed in mph you're going to get if the power of the car in horsepower divided by its mass in pounds is given by this. And this factor here, which we can calculate, is about somewhere between 270 or when we calculate we get 270, it's observed to be 225. Discrepancy is because we've been a bit idealistic. If we take into account that there's a small period of initial motion which is dominated by the frictional force, okay, which is just coefficient of friction times the weight, okay, this period will end when half mv squared becomes equal to the frictional force times some distance. And if we just work out where that's true and then put that distance into the velocity rule, we've got a new initial condition for the motion at constant power from that position. And that gives you the right answer. So it's a rather nice little mechanics problem of a different sort. And if you want to allow the mass to be a time variable, you'll find it also solves exactly. And you know the fraction of mass that's lost in this problem, so you can put it all together. Well, I think my time is just up, and I hope that I've given you some flavour for a lot of different places where there's often quite simple mathematics which can give you insights into what's going on in sport that you might not get in any other way. And if you're a competitor, you might even think that there might be something that you could learn to your advantage. Thank you.